Okay, hi. I want to thank the organizers for this great conference, other than the little hiccup. I also want to congratulate the Prime team for their accomplishments, and I look forward to seeing the telescope. I'm going to be talking about Roman and the kind of exoplanets it can find. This talk would have made a lot more sense if I had given it when it was originally scheduled, but nevertheless, I'm not forward to it. So, you know, this is a microlensing conference, which microlensing is a technique, it's not a science. So I like to start with the science, and the way I like to motivate the Roman Galactic exoplanet survey and the transit survey is that we really want to try to understand planet formation. It's one of the goals of exoplanet research. And if you think about it, if you believe in a bottom-up formation scenario for exoplanets, then you have to understand the physical processes by which micron-sized grains grow by sort of 13 to 14 orders of magnitude in size, or 38 or 41 orders of magnitude in mass, to the mature planets that we see today. And as you cross all of those orders of magnitude in mass and size, the physics that dominates how the particles, the pieces of planets come together changes. And that is kind of what the fundamental problem is, the difficulty is of understanding planet formation. So our way of trying to attack this is basically we come up with, or we, not me, people smarter than me like Doug Lynn and others come up with planet formation theories that predict the distributions of planets. And the hope is that the physical processes that are at work in bringing planet pieces together to the mature planets we see today are imprinted on the distributions of planets that we can observe now. So we heard from Doug talking about deserts or gaps in the planet distribution. There's been long a prediction that there should be a paucity of giant planets around low mass stars, others as well. So the idea is that we basically want to measure these distribution functions as accurately as possible over a broad a range of planet and host star properties as possible. And that is one of the main motivating reasons for exoplanet research. So, you know, you have to show this plot at every exoplanet talk. And so this is showing planet mass as a function of orbital period on the left, planet radius as a function of orbital period on the right, for known planets as of a couple of years ago, but the point is the same. And, you know, you can see there's all sorts of interesting features in this distribution, some of which might actually be telling us about the physics of planet formation, some of which might be selection effects. But what is very noticeable is that in the bottom right corner, there's not very many planets. And this lack of planets is almost certainly not real. The planets in our solar system all live in this basic area where we've detected very few other planets. But you know, these planets may very well tell us a lot about how planets form. And of course, the reason that we're not sensitive, you know, the few planets we have detected in that area have all been detected by microlensing. And so the reason we haven't detected a lot of planets there is just because the other techniques are typically biased against short period or massive planets or both. So I don't really need to tell the microlensing audience why microlensing is so great, but it's worth going through. We're sensitive to planets beyond the snow line, the place where we think planet formation is most efficient in a bottom-up planet formation scenario. Very low mass planets, long period planets, wide range of host masses, free-floating planets, giant moons, multi-planet systems, analogs of our own solar system, wide circumbinary planets, outer habitable zone planets, and planets throughout the galaxy. And the ones that I've shown in purple here are ones where we've actually detected those kinds of planets. Most of the ones that we know we have the potential to detect, but haven't yet, a lot of those will be enabled by Roman, and that's part of the reason why we want to do this. So I find it kind of amazing that we've detected so many of these very kind of unusual or exotic planets in the time since we've, in the however many 20 years since we discovered the first exoplanet with microlensing. Okay, so you heard from Julie about what Roman is. I'll tell you about the Roman Galactic Bulge Time Domain Survey. So this slide is outdated, as I'll talk about in a second. But nominally, this Roman Galactic Bulge Time Domain Survey is 7 fields for a total of roughly 2 square degrees. Those fields will be monitored in a wide filter, 1 to 2 micron filter, at 15-minute cadence, roughly 50-second exposures. And then observations at other filters, maybe at the cadence of every 6 hours, very much TBD, for 6 seasons of 62 to 72 days. And 72 days is basically the longest that you can look at the bulge with Roman. And so that adds up to about 41,000 exposures in this wide filter over 432 days spread over the 5-year mission. Okay, so I noted here, this is a notional survey. This is a survey a lot of us have been working on for a long time, mainly defined by Matthew Penny, which I'll talk about in a second. But I should mention that very recently, the Core Community Survey Definition Team has released their report. You can find it there. Their goal was to, their job was to collate a bunch of information from other people, from people interested in a wide range of science that you can do with the Galactic Bulge Time Domain Survey, and to come up with some strategy that optimizes or better optimizes the science you can do while still meeting the science requirements for the micron survey. And so, they presented 3 different scenarios: a nominal, underguide, and overguide. The parameters of those are listed here. They're somewhat different than the notional survey I just mentioned. I think one of the biggest difference to take away is that there will be one field at the galactic center. And this is made possible. We can still achieve our science goals in microlensing and add this field because the slew and settle times are less than what was assumed during Matthew's simulations. So that's fantastic. That's a lot of great extra science we can do. And then you can also see that the number of fields and the cadence changes depending on how much time the nominal, underguide, and overguide. And so these recommendations and now be given to the overall ROTAC, the Roman Telescope Allocation Committee, and they're going to decide between these 3 scenarios, taking into account the science that's possible with all the other core community surveys, the Galactic Plane Survey, and all of the general astrophysics that you can do as well. So stay tuned for that. I can answer some questions about why that was chosen, but if you really want to know those answers, you should ask Jessica Liu, who was on the survey definition committee. Okay, so the yield that we get from Roman is also based on end-to-end simulations. We have a galactic model. We assume properties of the galaxies and the lens stars and host stars, lens stars and source stars. We create simulated images. And then we inject those with microlensing events and then inject those microlensing events with planets and then find out how many we detect. And all of this work, I really want to emphasize, has been led by Matthew Penny based on his own simulation tool, which actually has heritage from when he was simulating the yields of Euclid for a Euclid survey like Roman. And I know there's people in the room who put the name on who were involved in that. And that was when he was a PhD student. So the yields, these are the nominal yields. This assumes a Kazan mass function. I'll talk more about that in a second. And so this is where this 1500 number that you've seen thrown around at this meeting comes from, is assuming that mass function in Matthew's simulations, including 50 free-floating Earths. I just want to emphasize, don't believe these numbers at all, because if we knew the answer to this, how many we would find, we wouldn't have to do the survey. It's obviously less uncertain towards the higher mass n because we do have some constraints from ground-based surveys, as we've seen. So, I think I'm really of various minds on how to present the yields now that we know from the great work of the MOA teams, the OVAL teams, the KN-TNet surveys, what the mass function is, at least to within a factor of several. We know what the mass function is. I recognize there's important discrepancies between these results that need to be ironed out. But the bottom line is it looks like at the low mass end, it's probably not as, these planets are not as common as was assumed in the Penny simulations. So the yield of planets is almost certainly going to be lower than 1500, unless there's a very sharp upturn in very low mass planets, which is possible. And that's not to say anything about free floating planets, which are probably much more common than was assumed in the Sampson-Johnson's paper that predicted the yield of those with Roman. Okay, so this plot you've seen many times. This is the basic, the plot you want to show anyone to sell the Roman mission. We don't need to sell the Roman mission. It's going to be launched in next year, as Julie likes to say. But it really is a very stunning plot. I just want to briefly talk about some of the other things. So Sampson-Johnson has been working on the yields of free-floating planets Again, we need to update these with the current, the best guess is what we have from the SUMI and KMTnet results. I just want to mention this, if you take so this plot is a little hard to understand, but it's the total mass in free floating planets per decade in mass. You can detect as a function of the mass of the free floating planet, given the nominal penny 2019 survey definition. So in other words, if there's a total of a tenth of an Earth mass in 0.1 Earth mass objects, you would be able to detect at least 3 of them. And so what you see is that the sensitivity goes down as you go to lower mass, or the limit goes down as you go to lower mass, and then it rises as you go to even lower masses than sort of Mars, and that's because finite source effects start to kill you. But there's still some sensitivity all the way down to Pluto. And so if you extrapolate the SUMI mass function, which predicts roughly an equal amount of mass per decade in mass of free floating planets, we would actually expect to detect a handful of Pluto mass planets. And this is with the nominal penny strategy. With some of the override strategies that were predicted, you might actually detect more. I think that's a really interesting result. It may end up being the most immediate and impactful result that we get from the RGES survey. We do have some potential sensitivity to potentially habitable planets, so we can get a better estimate of Eta Earth. We are sensitive to moons of giant planets. Matthew Lastowka has just submitted a paper on estimating the yields of these. They're not going to be a lot of them, but we do have sensitivity to them, so that's kind of exciting. Paper should be out in a month or so. Arjun is going to talk about circumbinary planets. The nice thing about microlensing is it's complementary to transits, and that we're sensitive to planets orbiting further out around circumbinary stars than transiting planets. And so I just want to spend the rest of my time talking about the statistical power of the Roman Galactic Bulge Time Domain Survey. So, we're looking at millions, hundreds of millions of stars down to say 23 magnitude. At nominally at 21.15, our photometric precision per epoch is 1% and 1 milliarc second. And then you have roughly 41,000 images. You expect tens of thousands of microlensing events. There's an enormous amount that you can do with all this data, besides 5 microlensing events. And so this is just a very small subset of the kinds of science that people have suggested we could do with this. I just want to highlight this one. It's been pointed out that you should be able to detect, and this goes all the way back to the initial simulations by Dave and Sun-Ri, that you should detect about 100,000 transiting planets. So these are simulations by Robbie Wilson showing transiting planets in the Roman data set, Galactic Bulge Time Domain data sets. This is showing the yield as a function of distance for different, broken down by size of the planet and by the spectral type and location of the galaxy. You can see those numbers on the left are large. So we expect about 100,000 transiting planets, which is amazing. What we can do with those, I don't know. Hopefully, Eamon will tell us after lunch. But this is the updated plot when you include the transiting planets, and I think this is even more powerful than the original penny plot, as I call it. Just showing that with Roman, we have sensitivity to basically all planets with mass or radius greater than that of Earth, or twice Earth maybe, or over all separations, and also in all major components of the galaxy. So if you just want to summarize what Roman can do for the demographics of exoplanets, by combining the transit and microlensing detections just within Roman, we'll get a nearly complete statistical sample of planets from semi-major axis from 0 to infinity, masses and radii greater than twice Earth, in the 3 major stellar components of the galaxy. And that, I think, is going to be amazingly transformative. How we actually get that information out is challenging, and I think deserves a lot of thought. Okay, so how much time do I have? I feel like I must already be over. 2 minutes. Okay, all right, good. Okay, so I am the PI, and Dave here is the science PI of the Roman Galactic Exoplanet Survey Project Infrastructure Team. This is a team of about 71 scientists located all over the world. Please raise your hand if you're a member of this. Okay, most of you, lots of you. And there's 12 working groups, and we are tasked to do a number of things. We are supported by NASA, thank you, Julie, and tasked to do a number of things. But I'd like to summarize that our scientific goal is to ensure that the RGES science objectives are met. And so that's to carry out the statistical census. But we also have broader goals. We want to build a large, vibrant, and diverse community of scientists and learners to actively engage with the RGES survey and the Roman mission. We want to inspire the public by sharing the exciting science discoveries that we have from the Roman survey. We also want to support the other science that can be done by the Galactic Time Domain Survey and support the Roman project itself and the two science centers, the Science Support Center and the Science Operating Center, and their tasks as well. So it's a very broad and intertwined community that's working hard to make sure that the science of Roman is maximized, not just the exoplanet demographic science. So here's some of our tasks. I won't go through these. We have lots of things to do on our to-do list. And I just want to end by saying, let us know if you want to get involved. There are various people in the room that are leading some of the working groups. I can point you in their direction. We now have a public website, finally, that you can look at, and it talks about the different working groups and kind of we're eventually populating it with what they're going to be doing. And, we have a Slack channel, and we have monthly meetings and all that good stuff. So let me know if you're interested in getting involved. We have a pretty open door policy. If you feel like you can contribute, just let me know or let Dave know. Thank you. So questions.
Well, I will make a question. So you emphasize the fact that in principle, we will be sensitive even to Pluto mass objects in floating planet countries. Then I remember a debate about the optimal cadence for such small objects. So maybe a higher cadence would be optimal to restore such very, very small objects. So, but now the nominal choice is actually for the same cadence as in the first design with 15-minute cadence. What would you comment about that?
Yeah, so I mean, I'd be interested to hear if Jessica has a comment on that. But my thinking on this is that, yeah, there's a paper by Andy Gould, people argue, that if you go to very high cadence, like 5-minute cadence or something like that, you can increase the yield of these very low mass, not just free floating Plutos, but anything that's very low mass, you would increase the yield of those things. But the thing is that actually comes at a cost, right? If you have a fixed cadence and you have an exposure time, your slew and settle times are set, and then also sets your number of fields. So if you have a higher cadence, you're going to and you want to have something that's nearly optimal, you're going to have a smaller number of fields. And that means you're going to lose science in the high mass end. So you might end up improving your yield of low mass planets by a factor of 50%, but you would decrease your yield of high mass planets by a factor of the ratio of the number of fields, which, for 5 minutes would be something like, 80% or something. So, there's a give and take there on what you want. I think one of the things I think a lot about is, I think it would make a lot of sense to do this survey, maybe tweak it a little bit for improving the yield of low mass things, see what we find, and then maybe in the extended mission, we can ask for a survey that's just 1 or 2 fields where we just hammer on those fields and really try to flesh out the demographics of these very low mass objects.
Yeah, clearly. Anyone comments? Question? Yeah, hi.
So you talked about giant moon. So we know the many giant planets have multiple moons.
Yeah.
Is that still possible to modeling?
So I mean, people have written codes that are able to do 4 bodies. Thank you. Are they? So I think if you have multiple moons that are roughly the same mass, and their mass ratio between them and the planet is 10⁻⁴, then you're probably in the superposition, approximately in the superposition regime, maybe depending on the separations. At least the results I've seen from working with Matthew Lastovka. And so there, I think maybe the problem isn't so hard, but I would say that deserves a lot more thought and work to see if we can really, there may very well be degeneracy that we aren't aware that could hamper the interpretation.
But they,
So, in your discussion of the moons, you mentioned, finding moons around giant planets. But if you look at our solar system, the most detectable moon would be the Earth's moon.
Right.
And I think this is relates to the mobile moons as well. The moons of Jupiter are certainly thought to have formed of the sort of planetary disk, which ends up appearing alongside the Einstein radius, like the Einstein radius of the planet. And the advantage of the Earth's moon is that it's close to like the Einstein radius of Earth.
Right. So, I mean, so in our paper, we focused on giant moons around giant planets because it was one thing to tackle. I think it's worth looking at giant moons around terrestrial planets. Those obviously formed in a very different way, as Dave mentioned. But they might be rare, right? It required a pretty unusual collision of something that had one third or something the mass of the Earth to make the moon. So, who knows? I think the one thing I would really say is that I am very leery of looking at the solar system and trying to use that to predict what other planetary systems are going to be like, because we've learned, if anything we've learned from exoplanets is that exoplanets are, Mother Nature is much more imaginative than we are.
Jessica, that's the last question.
So you talked about transiting exoplanets and microlensing exoplanets. Has anybody done a yield calculation for astronomical wobble exoplanets?
Oh, you mean really just direct astrometry? Not that I know of. Would be interesting. Yeah, I would say, and I'm not just saying this because Jessica asked me a question. I would say that the astrometric potential of the Roman Galactic Bulge time domain survey has not been explored to nearly the level of the photometric potential. And I think it's definitely worth thinking much more carefully about what we can learn from the astrometry. I mean, I didn't even mention astrometric microlensing, which might be able to get us down to not just black holes and neutron stars, but according to people that know better, like Jessica, might be able to get us down to half solar mass hosts, which would be transformative in my opinion.
So actually, I mean, there is a paper on discovering planets by astrometric, nearby astrometric, astrometric signals from the Roman wide-field instrument. I think it's led by a cosmologist who's,
Yeah.
And so,
That was.
as far as I know, no one has really followed up on that serious analysis, but that could be a really good.
Yeah, those are really bright stars. They were going to use the diffraction spikes to do that. Very complementary to the bulge.